Hi, my name is Gerardo Vega, professor of the Universidad Nacional Autónoma de México, and I'm going to talk about a characterization and an explicit description of all primitive polynomials of the degree 2. However, before we started, it is important to say that this talk is based on this recently forthcoming paper. Thus, any of you that wishes to go deeper in this talk, this paper is useful. In fact, this is an open access paper that is now available on the homepage of the journal Finite Fields and their application. Let's get started, and we are going to start by presenting the motivation of this talk. Thus, let f of x be a monic polynomial of the degree 2 over the real numbers given by x squared plus bx plus c. Then, it is well known that the polynomial f of x is an irreducible polynomial if and only if b squared minus 4c is a negative number. That is, if this square root does not belong to the real numbers. Now, suppose that f of x is an irreducible polynomial over the finite field fq. Thus, the question is, could there be a similar test in terms of the two coefficients b and c to determine whether or not f of x is a primitive polynomial? That is, f of x is a primitive polynomial if and only if the two coefficients b and c satisfy some test to be determined. This question was what encouraged our study and has approached toward a solution. We found, number one, a new characterization for all primitive polynomials of the degree 2 that improves the Fitzgerald characterization. Later on, we are going to recall such characterization. Number two, as an interesting byproduct of this new characterization, we also found an explicit, complete, and simple description of all primitive polynomials of the degree 2 over any finite field. In order to present such results, this talk is divided in 7 sections. Thus, in the first section, we are going to establish our notation and recall some key definition about primitive polynomials. In section 2, we are going to record the Fitzgerald characterization. In section 3, we are going to present 3 preliminary results. Section 4 will be devoted to present our characterization, while in section 5, we are going to compare the two characterizations. In section 6, an explicit description of all primitive polynomials of the degree 2 will be presented. Finally, section 7 will be devoted to present our conclusions. Now we are going to establish our notation. Thus, from now on, q is a power of a prime number, and by using fq we will mean a finite field with q elements. A primitive polynomial of the degree k over the finite field fq is an irreducible polynomial that has the property that any of its roots can generate all the non-zero elements in the finite field extension fq to the k. In fact, in a more precise way, if f of x is a polynomial of the degree k and f of alpha is equal to 0 for some root alpha, then f of x is a primitive polynomial if and only if its root alpha generates the multiplicative structure of the finite field extension fq to the k. Now, related to any polynomial, we have the following definition. Definition 1. Let f of x be a polynomial of positive degree with f of 0 different to 0. Then the last positive integer e for which f of x divides x to the e minus 1 is called the order of f of x and denoted by order of f. The following is a well-known characterization of the primitive polynomial, which can be seen as an alternative definition in terms of the order of a polynomial. Theorem 1. Let f of x be a monic polynomial of the degree k with f of 0 different to 0. Then f of x is a primitive polynomial if and only if its order is equal to q to the k minus 1. The following definition, close related to the order of a polynomial, will be of great importance for this talk. Definition 2. Let f of x be a polynomial of positive degree with f of 0 different to 0. Then the last positive integer root for which h to the root is congruent modulo f of x to some non-zero element A in the finite field FQ is called the quasi-order of f of x and denoted by q-orth of f. Now, in terms of the quasi-order of a polynomial, the following is a quite useful characterization of primitive polynomials. Theorem 2. The monic polynomial f of x of the degree k greater than or equal to 1 is a primitive polynomial over the finite field FQ if and only if minus 1 to the k times f of 0 is a primitive element in the finite field FQ and his quasi-order is equal to q to the k minus 1 divided by q minus 1. Now we are going to recall the Fitzgerald characterization. Theorem 3. Let f of x be an irreducible polynomial of the degree k over the finite field FQ. We set m equals to q to the k minus 1 and define the polynomial g of x given by this polynomial division. Then f of x is a primitive polynomial if and only if the polynomial g of x has exactly this number of non-zero terms. Let's see an example. We take q is equal to 5 and note that the polynomial f1 given by x squared plus x plus 1 and the polynomial f2 given by x squared plus 3x plus 3. These two polynomials are irreducible over the finite field f5. Also, note that k is equal to 2 for this example, m becomes 24, and this value for this example is equal to 19. Now, it is not difficult to see that the polynomial g1 of x given by this polynomial division has a non-zero terms, while the polynomial g2 of x given by this other polynomial division has exactly 19 non-zero terms. Therefore, by Fitzgerald characterization, f2 is a primitive polynomial while f1 is not. Now we are going to present three preliminary results. Thus, the following two propositions are essential to obtain a new characterization of all primitive polynomials of the degree 2. Proposition 1. Any irreducible polynomial of the form x squared plus minus bx plus c over the finite field FQ divides the polynomial x to the q plus 1 divided by c. In addition, if the polynomial x squared plus bx plus c is a primitive polynomial, then his linear coefficient b must be different to 0, and his constant coefficient must be a primitive element in the finite field FQ. Finally, x squared plus bx plus c is a primitive polynomial if and only if x squared minus bx plus c is also a primitive polynomial. Let's see an example. We take q is equal to 5 and clearly q plus 1 is equal to 6. And it is not difficult to obtain that x to the 6 minus 1 can be factorized in this way. Will x to the 6 minus 3 can be factorized in this other way. Therefore, by proposition 1 and example 1, observe that these two polynomials are primitive, while these other three polynomials, these three irreducible polynomials, are not primitive. This irreducible polynomial and this irreducible polynomial and this other irreducible polynomial are not primitive. Proposition 2. Let f of x be a monic polynomial of the degree 2 with f of 0 different to 0, and assume that x to the root is congruent to a modulo f of x for some non-zero element a in the finite field FQ, where root is equal to the quasi-order of f. We also take the polynomial g of x given by this polynomial division. Thus, our proposition asserts that all the terms in our polynomial g of x, all his terms must be different to 0. Our last preliminary result is the case to obtain an explicit, complete, and simple description of all primitive polynomials of the degree 2. Proposition 3. Let f of 1 given by x squared plus bx plus c and the polynomial f2 constructed in terms of the polynomial f1 in such a way that, as we can see here, the linear coefficient is multiplied by m to the j, and the constant coefficient is multiplied by m to the 2j, where j is a positive integer and b, c, and m are non-zero elements in the infinity field. Then our proposition, the proposition 3, asserts that these two polynomials, the polynomial f1 and f2, constructed in this quite particular form, must have the same quasi-order. Let's see an example. We take now q is equal to 11 and the polynomial f1 given by x squared plus 5x plus 2. Then it is easy to see that the quasi-order of f1 for this example is equal to 12. Now, if j is equal to 1 and m is equal to 4, the polynomial f2 becomes equal to x squared plus 9x plus 10. And by our proposition, we can be sure that these two polynomials, f1 and f2, have the same quasi-order, which is equal to 12. However, it is not difficult to see that the order, not the quasi-order, the order of f1 is equal to 24, while the order of f2 is equal to 120. And this means that proposition 3 preserves the quasi-order, but not the order of polynomials of the degree 2. Now it is time to present our characterization. Thus, let f of x given by x squared plus bx plus c be an irreducible polynomial over the infinity field fq. Now, if q plus 1 is not a power of 2, then we take the integer e given by q plus 1 divided by p, where p is the smallest odd prime number that divides q plus 1. And by the division algorithm, we also take the polynomial h of x and the polynomial r of x to be the quotient and the remainder of the division of the polynomial division of x to the e plus 1 divided by the polynomial f of x. Thus, observe that our polynomial h of x can be written by means of this polynomial division. Then, our characterization says that f of x is a primitive polynomial if and only if its linear coefficient is different to 0, his constant coefficient c is a primitive element in the infinity field fq, and at least one of the following two conditions holds true. Condition A: q plus 1 is either equal to a power of 2, or q plus 1 is equal to a prime number p greater than 2, or q plus 1 is equal to 2 times a prime number p greater than 2. This is condition A. Condition B says that all the terms in our polynomial h of x must be different to 0. The following is a sketch of the proof. By proposition 1, a necessary condition in order that f of x be a primitive polynomial is that b is different to 0 and c is a primitive element in fq. Now, if condition A holds true, then we take r to be a root of the polynomial f of x. Since b is different to 0, it is not difficult to see that r, the root r, is actually a primitive element in the infinity field fq squared, and therefore f of x is a primitive polynomial. Instead, if condition B holds true, then by proposition 2, it is not difficult to conclude that f of x is a primitive polynomial. Let's see some examples. Let q is equal to 5, let q is equal to 5, and we take again, as in example 1, the same polynomials. Thus, we take f1 given by x squared plus x plus 1, and f2 given by x squared plus 3x plus 3. Since q plus 1 is equal to 6, we see that condition A holds true in our characterization, and note that this constant coefficient is a primitive element in the infinity field f5. Well, this constant coefficient is not, because it's 1. 1, of course, is not a primitive element. Thus, this constant coefficient is not a primitive one. Thus, we As in example 1, we conclude again that f2 is a primitive polynomial while f1 is not a primitive polynomial. However, observe that we arrive at the same conclusion as in example 1, but we arrive to such conclusion without need to do any polynomial division. Let's see another example. We note that q is equal to 11 and note that 2 is a primitive element in the finite field F11. Since q plus 1 is equal to 12, p is equal to 3 and the integer e becomes, for this example, equal to 4. Now it is easy to see that this polynomial division has exactly 4 non-zero terms, while this other polynomial division has only 3 non-zero terms. Thus, by condition B, these two polynomials are primitive, while these other two are not. In fact, these two polynomials are not primitive because despite that his linear coefficient is different to 0 and his constant coefficient is a primitive element, any of these two polynomials does not satisfy the condition B in our characterization, as we can see in this polynomial division, where we get for this polynomial division only 3 non-zero terms, where we expect to get 4 non-zero terms. Now it is time to compare the two characterizations. Thus, note that the Fitzgerald characterization and our characterization are similar in that both rely on the evaluation of polynomial long divisions. However, the polynomial long division in condition B of our characterization involves a divided polynomial whose degree q plus 1 divided by p plus 1 is significantly smallest than the degree q squared minus 1 of the divided polynomial in the Fitzgerald characterization. This difference can be appreciated in examples 1 and 5. In addition, as is shown in example 4, condition A in our characterization identifies in a quite easy way those finite fields for which it's not necessary to evaluate a polynomial long division to determine whether or not an irreducible polynomial is primitive. In fact, in order to appreciate the useful of condition A, in this table it is shown the first 12 finite fields that satisfy such condition. Now, at this point of the talk, we want to find an easy way to determine whether or not a polynomial of this quite particular form is an irreducible, where alpha is a fixed primitive element in the finite field of Q and the exponent I is an integer number taken in this interval. To this end, and if Q is even, we define the following disjoint integer sets: the set capital R0 and the set capital B0, defining in this way. And as we can see, these two sets are indeed disjoint, and his union, the union of these two sets, gives us the set that goes from 0 to Q minus 2. On the other hand, if Q is odd, we define instead the set capital R1 and the set capital B1, defining in this way. And again, these two sets are disjoint, and his union gives us the set that goes from 0 to Q minus 1 divided by 2 minus 1, where, as usual, E modulo Q minus 1 divided by 2 is the remainder of the division of I by Q minus 1 divided by 2, and B between these two brackets is the largest integer less than or equal to B. Now we introduce the Boolean variable delta, defining in this quite simple way. Delta is equal to 0 if Q is even, and delta is equal to 1 if Q is odd. Thereby, by the way the set capital B0 and capital B1 were defined, it is not difficult to see that this polynomial with this quite particular form is an irreducible polynomial if and only if the exponent I belongs to the set capital B delta. Let's see some examples. Example 6. we take f8 constructed in this way and note that alpha is a primitive element in the finite field. Then it is not difficult to obtain that capital R0 for this example becomes equal to 0, 2, and 3, and therefore capital B0 becomes 1, 4, 5, and 6. Thus, these three polynomials whose exponent in alpha is in blue, these three polynomials are reducible, while these other four polynomials whose exponent is now in red, these four polynomials are irreducible. Let's see another example. We now take f9 constructed in this way and again observe that alpha is a primitive element. For this example, q minus 1 divided by 2 is equal to 4, and q minus 1 divided by 4 between these two brackets is equal to 2. Then it is not difficult to obtain that capital R1, for this example, capital R1 is equal to 0 and 3, and therefore capital B1 becomes equal to 1 and 2. Thus, these four polynomials are reducible, while these other four polynomials are irreducible. Now it is time to present an explicit description of all primitive polynomials of the degree 2. However, before going deeper, we are going to assume that alpha is a fixed primitive element in the finite field of Q. Thus, with this in mind, we need to introduce some new integer sets. The first one is the set capital I delta defined in this way, and as we can see, such set is indeed a subset of the set capital B delta. Now, observe that the set capital I delta can be obtained in a relatively easy way by means of our characterization, and if condition A holds true, then we directly have, without need of to do any polynomial division, we have that our set capital I delta is actually equal to the set capital B delta. Now, if Q is 7, then we are gonna need also the set capital G0, which is defined in this way. And if Q is odd, we are gonna need instead the set capital G1 defined in this way. With this set in mind, we are not in condition to present an explicit, complete, and simple description of all primitive polynomials of the degree 2 over any finite field. Theorem 5. Let capital I delta and capital J delta be as before. Then any primitive polynomial of the degree 2 over the finite field of Q can be obtained by means of this quite simple expression, where the exponent I is taken in capital I delta and the exponent J is taken in capital J delta. The following is a sketch of the proof. Let I an element in the set capital I delta. Since this polynomial with this particular form is a primitive polynomial and therefore an irreducible polynomial by hypothesis, it is not difficult to see that this other polynomial with this other form is also an irreducible polynomial if the exponent J is taken in capital J delta. Now, by using proposition 3, it is not difficult to see that these two polynomials have the same quasi-order, which is equal to Q plus 1. On the other hand, for the way the set capital J delta was defined, note that the element alpha to the 2J plus 1 is a primitive element in the finite field of Q if and only if the exponent J is taken in the set capital J delta. Thus, by theorem 2, this irreducible polynomial is actually a primitive polynomial. Let's see some examples. We take f8, we again take f8 constructed in this way, and by example 6, in which example we already found that capital B0 is equal to 1, 4, 5, and 6. And by means of condition B of our characterization, it is not difficult to obtain that capital I0 is equal to 1, 5, and 6. And as we can see, really the set capital I0 is indeed a subset of capital B0. Since capital G0 becomes equal to 0, 1, 2, 4, 5, and 6 for this example, we have, in accordance with our theorem phi, that the 18 primitive polynomials over F8 can be obtained by means of this simple expression where the exponent I is taken in capital I0 and the exponent J is taken in capital G0. Now, observe that if phi denotes the Euler phi function, then the number of primitive elements in the finite field F8 square is equal to phi of Q square minus 1, which becomes 36 for this example. And in consequence, the total number of primitive polynomials of this degree 2 over the finite field F8 is equal to 36 divided by 2, which of course is equal to our 18 primitive polynomials that we already found by means of this quite simple expression and by means of these two sets, the set capital I0 and the set capital G0. Let's see another example. We now take F9 constructed in this way, and by example 7, in such example we already found that capital B1 is equal to 1 and 2. And since Q plus 1 is equal to 10, then we have that condition A in our characterization holds true, and therefore, as we already say, under such condition, the set capital I1 becomes equal to capital B1, and therefore we don't need to do any polynomial division in order to obtain or find the set capital I1. On the other hand, it is not difficult to see that for this example, capital G1 is equal to 0, 1, 2, and 3. Thus, in accordance to our theorem phi, the 16 primitive polynomials can be obtained by means of this simple expression. Again, note that phi of Q squared minus 1 divided by 2 is equal to 16. Now we are arriving at the conclusion of the talk. Thus, for polynomials of the degree 2 over finite fields, we present in Theorem 4 a new characterization of primitive polynomials. This new characterization is substantially improves upon the Fitzgerald characterization because for primitive polynomials of the degree 2, the degree of the divided polynomial in a polynomial long division is considerably reduced in this new characterization. As an interesting byproduct of this new characterization, we also obtain, in Theorem 5, an explicit, complete, and simple description of all primitive polynomials of the degree 2 over any finite field. As a continuation of this work, we believe that it will be interesting to improve Theorem 4 and 5 in order to extend our current study to primitive polynomials of the degree greater than 2. Finally, as a matter of certainty, the results in this research can also be used to obtain the complete weight distribution of some family of irreducible cyclic codes of dimension 2 over any finite fields. And that's all, so thank you very much. Molto obrigado. Muchas gracias.